All right, let's do another geometry. Gauss's law for a plane of charge. Okay, so I'm going to draw the plane. I'm going to draw it as sort of a cut, a cross-sectional cut, like this, and I'll give it a little bit of thickness just so that you can see it. And this is the plane in cross-section. I'm going to draw sort of a little bit of a visualization of it sort of going off in 3 dimensions. We don't need to go to the visualization lab. You get the idea. This is a plane going back into space. It has a charge density sigma. So sigma coulombs per meter squared. And in a Gauss's law problem, first thing we always ask is, what does the symmetry tell us? So in this case, when you have a plane of charge, the symmetry is actually telling you that the E field points normal to the plane. So if I were to put a coordinate system like this, where I have x and y like that, the plane is in the xy, the plane of charge is in the xy plane, then the E field is going to point in z. And you could say, well, what if you come over here? Now it's no longer symmetric because we have more charges over here than we have over here. But actually, we're not just doing this plane of charge. We're doing an infinite plane of charge. Gauss's law, as we're using it here, only works for an infinite plane of charge. Gauss's law works for anything, but for the way we are doing this calculation, it has to be infinite. Okay? Therefore, since the plane actually goes on forever, it's also true that the lateral components of the field cancel. E is also perpendicular to the field here, and it's also perpendicular to the field here. And if you go under the plane, it's perpendicular, but it's going to be down, assuming that's positive charge, and it's going to be down like that, and it's going to be down like that. So basically, symmetry tells us quite a bit. It says that the plane makes a field pointing away from the plane. Okay? So E will be along the z axis. So now that you know that, you need to pick your Gaussian surface. Okay, so let me erase some of this stuff here. Don't need all these. So you actually have 2 choices for your Gaussian surface, and you want to think in terms of symmetry. What do you want? You want faces on the surface that are either perpendicular to the E field, so that their area vector will be along the E field, or you want faces that are sort of parallel to the E field, so that their area vector will be perpendicular to the E field. That's the 2 main things you want in a Gaussian surface. So one of them would be this. Here is a cylinder with a top. It comes down and it pierces the plane there, and it keeps going, and it kind of looks like that. And if we could see through the cylinder, the bottom would look like that. So that's a Gaussian cylinder. And that is one good choice for a plane. But you'll also see this. You'll see what's called a Gaussian pillbox. Now, pillbox is sort of this thing that sometimes a silly word just sticks in physics, and we use it over, and every book uses it, and everybody uses it. And I'm worried some of you might not know what a pillbox is, especially because you're young and you don't need a pillbox yet. Well, I have a pillbox. So this is my pillbox. I got it in San Antonio at the Alamo, and it really is literally, it just means a box. In physics, pillbox just means a rectangular prism. It's just something with 6 sides and right angles on it. That's all it is. This pillbox is important to me because it helps me remember to take my meds, and it helps me remember the Alamo. It sort of does both of those in one thing. So all a pillbox is a little teeny box. Okay? So here we're going to draw a Gaussian pillbox that looks like this, like that, and it comes down like that, pierces the plane, keeps coming down like that. And we could draw the back surface like that if we wanted to, and it would go up. So it's basically just sort of a cube sitting in the surface. Okay? So either one will work. And we're going to do the integral, and it won't actually even matter which Gaussian surface we're using. Okay? So let's see. Gauss's law. Integral of E dot dA is the charge enclosed over epsilon naught. I'm going to write that so many times to make sure you memorize Gauss's law. So when we have the integral around a closed surface, the way we do the integral is we break it up into the individual surfaces. Right? So each one of these actually has sort of 3 kinds of surfaces. They have a top that has its area vector in one direction, they have a bottom that has it in the opposite direction, and they have sides, which in terms of Gauss's law are actually equivalent, because the sides all have area vectors that point perpendicular to the E field. So we could actually just say this is the E field of E dot dA of the top plus the integral of E dot dA of the sides plus the integral of E dot dA of the bottom equals the charge enclosed over epsilon naught. Okay? And then you just look at it and you figure out what those are. And since we've set it up with symmetry, it's not too bad. We could say these surfaces have a top area A, like that. And that's actually all we need to know. We don't even actually care what the length is. You'll see it doesn't matter. So the flux to the top, well, E is up, and the A vector, if we drew it as a vector, is also up. So the angle between them is 0. The dot product is gone. It's just E times dA. E is also constant. If you move around on this surface, E doesn't change as you move around above a plane. It might change if you move away from the plane. We'll see. But moving laterally makes no difference whatsoever. So in that case, this integral just becomes E times the integral of dA. Well, the integral of dA is just that area. So this one just becomes EA. So that's a case where we use symmetry to set up the integral to make it easier. The sides always have their A perpendicular to the E field. Right? Here it comes out, here it comes this way. Therefore, the dot products all give you 0. Right? So the sides don't contribute. The bottom surface has its A going down like that, because remember the area vector always points to the outside. Here the area vector points down. But the E field also points down. If we think about symmetry, here the E field points up, on this side the E field would point down, so it's actually EA again, it's positive flux again. Okay? So there's the integral side of the equation. The other side is the charge enclosed. The charge enclosed is that area times the charge density, right? Because the actual piece here that's enclosed looks like that. It's just, in this case, it's a circle with area A. In this case, I didn't leave myself a lot of room to draw it, but it's a square with area A. So it's just sigma times A over epsilon naught. Okay? So EA plus EA is 2EA, and if you want to, and then the A's cancel, right? So in the end, what you get is that the electric field is sigma over 2 epsilon naught. And if you want to think of it in terms of a vector, you could add a vector, and over the top, it would be in the z direction, and underneath, it would be in the negative z direction. You can't actually write one expression for it, because it's not always pointing the same way. It kind of depends on what side you're on. But here we've solved for the magnitude of the electric field. It's the electric field magnitude is sigma over 2 epsilon naught, and the direction depends on what side of the plane you're on. What's interesting about that is that it doesn't depend on how high you are above the plane. Notice we didn't put a length in there. We could have put an L for the height of that thing, or an L for the height of that thing. It wouldn't matter. We never needed it. Right? We never did anything. No part of the integrals needed that L. The only part that involved L, the integral was 0. So what that tells you is the E field is constant everywhere above the plane. No matter how far you go away, it's the same E field. No matter how close you get, it's the same E field. When we talk about, in other parts of the class, here's just a uniform E field, you might think, how did they make that? Well, you could make it with just a uniformly infinitely charged plane. Okay? So I see that we do have a question here. Let's see. Andrea Plan B, why isn't the field infinite on the surface? Why is it? Oh, okay, yes, I've seen this question before. I can tell you why. Very good question. Comes up a lot and actually illustrates almost perfectly a very important point. Let me erase the integrals and draw a little bit more. Okay. So what Andrea Plan B is asking is basically this. Here we have the plane and it's charged. Okay, we're looking in cross section again. And I'm telling you that the E field has a value there, it has a value there, and it has the same value here. And even if you go down within just 1/100th of a nanometer to the surface, it's still got the same value. which seems strange because there's charge here. And when we think about Coulomb's law, when you get really close to charge, the field's supposed to get really big, right? For a point charge, it goes to infinity. So how is it that we can get so close to charge and never actually have a large E field? Okay? And the answer is that our model doesn't let us get close to a charge. This is a limitation of our model. Remember before when I said when you make a model, it's never always accurate, okay? So if I were actually going close to a real object that was essentially a plane of charge, and I eventually got close enough, I would see individual electrons. And if I got close to one of those individual electrons, the field would get really big, okay? So here, this is reality, is individual electrons. In the model, there are no electrons. The charge is smooth. So if I get really close, say this distance is 10 to the minus 5,274 meters. That's really close, okay? If I get really close, the charge that's really having the biggest influence is sort of this charge here and sort of this little cone, this little area right below the point I'm asking about. All the rest basically gives you lateral components that cancel. The charge that really creates this field sticking up shrinks to a ridiculously small value, okay? The amount of charge here is basically sigma times that area right there. That goes to 0 as this separation goes to 0. And since they both go to 0 together, the field stays constant. The field never blows up because you get closer and closer, there's essentially no charge underneath you. The field doesn't go to 0 because as you get closer and closer, you're closer and closer. Okay? So it does actually jive with Coulomb's law. If you remember that you're doing a model, you're not really doing reality. So that's a good question, and that's why you got to keep an eye on your models.